Hi, everyone, and thank you for joining today. My name is Nick Capelli, and I'm a Senior Application Engineer here at Parker Lord. Today, I'll be taking you through our presentation, Innovative Thermal Interface Materials, How Adhesives and Gap Fillers are Accelerating xEV's, the 4 Trends in Thermal Management. Today, we're going to be covering 4 major topics: EV battery serviceability, reworkability, low-density materials, and finally, alternate chemistry materials. Speaking first on Parker Lord, you may be familiar with our previous company name, Lord Corporation. At the end of 2019, Lord Corporation was acquired by Parker Hannifin, so now we're part of the Parker family, which as you can see is a very global company across 50 countries with 290 manufacturing plants. So this means that we are a global business with a local focus. Now moving to Parker Lord specifically, we're a collaborative partner with global support. Our goal is to deliver solutions to help meet your specific needs, and we can support you globally with our manufacturing capabilities around the world. You can see this manufacturing capacity is present in a number of continents around the world. Most of the materials that we will be discussing today are made in Indianapolis, Indiana, in Sagertown, Pennsylvania in the United States, Hückelhoven, Germany, or Shanghai in China. Talking about our expertise, we participate in a number of markets around the globe, most notably automotive, as EVs are the big trends right now. The key products in all of these markets are in the list below, but from this list, we'll be focusing mostly on thermal management, electronic materials, adhesives, and coatings. So let's start with trend number 1, serviceability. Defining serviceable versus non-serviceable is somewhere I'd like to start first. Serviceable materials are materials that are able to be removed, reworked, and repaired, which is extremely useful for the aftermarket, as we'll discuss later. Non-serviceable materials, on the other hand, are materials that remain in their place for the life of the part. So why is serviceability important? The reason behind this is that batteries are the most expensive aspect of an EV, and even something like small damage can render the battery cells inoperable. Of course, an inoperable battery cell means that if this occurs in production, an OEM has to scrap that part. And then of course, if a battery cell is rendered inoperable after the car has been purchased, then that means the consumer has to bring it into the shop to get repaired. If instead of having to replace the whole battery pack, an OEM can replace a single cell or a single module, or the consumer can get a single cell or single module replaced, this is going to allow for a lower cost on both ends, which ultimately, if cost is a concern for people who might not have bought EVs previously, knowing that the repair costs will be lower with serviceable materials may drive EV sales higher. So next, looking at challenges to serviceability, there are 3 major challenges that are listed here, and we will go and talk about these in more detail later on in the presentation. And finally, for materials that adhere too well, deformation of the cooling plate can occur during maintenance. So the desire for most repair shops and OEMs is to have low pull-off stress materials. Once again, we'll talk about this more in the coming slides. So starting first with serviceable sealing solutions. There are a number of different types of seals that can be used in an EV to help promote serviceability. You have perimeter seals, coolant and oil seals, and port and connector seals. And as you can see, there are elastomeric components that are easily reworkable, replaceable, removable. Now speaking on installation, to use these serviceable seals, there are 2 volumes you might see. First, in high volume manufacturing, you're likely to see semi-automated processes for putting these seals in place, something like a mandrel and a press. Whereas in low volume applications, you may just see manual installation, as in the picture on the bottom right, where they're just using their fingers to press the seal in place. This is important for low volume because it doesn't require a huge capital investment to still replace the seals properly. Now speaking on serviceable gap filler solutions, Parker Lord offers a number of serviceable gap fillers, and as you can see, they're listed here in this table. The idea here is that we're trying to lower the value of pull-off stress as much as we can so the batteries can be more easily removed from the battery pack, so then the gap filler, if there's a damaged cell or damaged module, can be scraped away, reapplied, and the new fresh battery cell or battery module can be placed on top of that newly dispensed gap filler. Our goal for our next generation of Cooltherm gap fillers is that they will have 25 to 40% less pull-off stress than the numbers above. So how do we go about measuring serviceability of gap fillers? This is done by vertical pull-off tests. As you can see on the picture on the left, we have a T-bar, and then we adhere a disposable aluminum plate to this T-bar using one of our structural adhesives, MaxLock MXT6, which is an acrylic structural adhesive. Then you can see we end up with what's pictured in the middle. This allows us to have space on either side of that disposable aluminum plate, so we can add spacers to dictate bond line thickness. Then, as you can see in the picture on the far right, we've now dispensed the gap filler, and then we place another T-bar on top with spacers on each side. And once the material cures in between those T-bars, we pull them apart, giving us the results of pull-off stress for these tests. Now let's move on to non-serviceable materials. So when are non-serviceable materials used? Typically, we would say that they are going to be used intra-module, meaning between individual battery cells and the module housing or heatsink. The idea here is that the non-serviceable materials can provide structural support to the individual battery cells, but then in conjunction, each individual battery module will be connected to the active cooling system or cooling plate with a serviceable gap filler. That way, even if an individual cell goes bad, again, instead of replacing an entire battery pack because one cell goes bad, you can just replace the module where that cell goes bad. As a result, this does still allow for maintenance of the cells. As far as how a manufacturer is going to be choosing serviceable versus non-serviceable materials, it's going to be dependent from person to person, though typically this is going to be driven by cost. One of the benefits is that non-serviceable materials eliminate the need for mechanical fasteners within each module. So sometimes this savings of mechanical fasteners in both weight and cost can drive the decision to use non-serviceable materials intra-module. Other times, however, they determine that the serviceability is more valuable than the idea of replacing those fasteners. So looking at our non-serviceable gap filler solutions, on the right is a video of Cooltherm UR2000 being dispensed from one of our MMD units in our lab in Cary, North Carolina. This is a 2-watt urethane gap filler with a 1:1 mix ratio. It's UL94V0 rated, assured D55 hardness, and has good adhesion to powder-coated aluminum. We're seeing urethane gap fillers pick up traction as being more popular in EVs, especially in the non-serviceable solutions, because urethanes generally have better adhesion than silicones. And in addition, urethanes do not produce volatile siloxanes. Now, volatile siloxanes have the reputation of preventing the adhesion of coatings or paints or other adhesives to the substrates that they should be attached to. So by eliminating the potential for volatile siloxanes to be present in manufacturing processes, urethane gap fillers just give OEMs more comfort. And we'll talk more about this in trend number 4 later on in the presentation. Now, in addition to non-serviceable gap fillers, we also do offer non-serviceable adhesive solutions. And these are listed here on the left. The first is going to be kind of the material that started it all, our Cooltherm TC2002. This is a 1-watt acrylic structural adhesive that's typically used to bond individual battery cells to the heatsink or cold plate in EV battery pack applications. Next, we have Lord AC902LC. This is a UV cured adhesive, non-thermally conductive, typically used to bond clear plastic substrates to the outsides of battery cells for extra structural support. Next, we have MaxLock MXT6 and Lord 5206. These are both acrylic structural adhesives that are typically used to bond metal and plastic housings, once again, for support to the battery pack. And finally, we have Lord 7545, which is available in many different curing speeds, which is used primarily to help bond plastic supports to the battery pack. So now that we know about all of these non-serviceable solutions, the next question you might have is, Well, at the end of life, how do we disassemble these battery packs? So let's talk about it. Introducing Lock Release 800. So this is a material that we qualify as a stripping solution. The idea here is you have a solvent-based material that is meant to remove cured, typically non-serviceable materials from their substrates. The pictures on the right are actually small coupons that are bonded together with TC2002. As you can see here, they're soaked in this vial, and then after a certain amount of time, the adhesive actually dissolves, allowing for the metal substrates to be separated. This material is very effective at removing acrylic, urethane, and epoxy materials from their applications. Speaking specifically on the process, these are the 4 major steps that you'll want to use when using Lock Release 800. The first, of course, for safety, is to ensure that all batteries are completely discharged. This way, you're not at risk of electrocuting yourself while taking apart the pack. The second then is that you're going to remove the parts and place them inside a bath of this lock release. After the parts have been added to the bath, next you'll want to add some sort of vibration or agitation to help speed the process up. Next, you'll want to cover the bath, and this is to prevent evaporation of the solvent within the stripping solution. And then, of course, you should cover it with an inert gas to make sure there's no risk of flammability. Then finally, you'll want to soak the parts for a specific amount of time, and after that time has passed, you can remove the parts and then start disassembling the battery pack. Next, let's discuss trend 2, reworkability. So first, in discussing this, let's define reworkability and why it's important. First, reworkability is defined as the ability for materials to be effectively removed, reapplied, and repaired. So looking at this slide, we'll be talking about reworkability at the module or cell level. As you can see here in this picture, we have a battery pack that is going to be outlined in green, and the battery pack is comprised of individual modules outlined in blue, and then those individual modules are comprised of cells outlined in pink. So the reason that we'd like to talk about reworkability on the module or cell level is because replacing a battery pack is going to be extremely expensive, and we'll talk about that more later. But the driving cost of all of these EVs is the battery pack. It's going to account for 25 to 40% of the electric vehicle. So if we can avoid replacing an entire pack anytime something goes wrong, and instead can replace something at the module or at the cell level, it'll be much easier for consumers, for OEMs, and much less expensive for both parties as well. The challenges, of course, though, are that these liquid dispense solutions are meant to eliminate all the airspace or air gaps in between the heatsink or the cooling plate and the modules and the cells. So you have to have some sort of compromise of a good performing material that's going to be easy to remove, but yet still has enough adhesion to keep the cells and the modules in place. And in addition, we also need to think about how can this rework be done efficiently out in the field, such as at an auto body shop. So talking more about reworkability, I think it's really important that we put numbers to the cost of reworkability. So looking here, there were about 2.1 million EVs in the market in 2019. And if we assume a modest failure rate of about 1%, that means that there were about 21,000 vehicles with issues. So if we look at replacing the entire battery pack when an issue arises, as opposed to replacing just the faulty module, which we'll say is about 8 cells per module in that battery pack, that could be a difference of approximately $200 million per year in repairs. So how do we quantify reworkability? As you can see here in the top right, we have a picture of a battery module. This will be our 2-dimensional version of this setup, of course, the 3-dimensional version to your left. So looking at this, we have a length of the battery module that's going to be defined as L. We have a height of the battery module, that will be H. And then we have a width between the modules, and that's going to be W. So looking at this, we have 2 ways that we can try to remove the battery module. The first is something that we'll call edge pull-off. So edge pull-off will have an angle of pull-off associated with that. We'll call that theta. There will be a distance that the edge of the module travels. That will be defined as x. But then, of course, you can see At a certain angle theta and with a certain distance x traveled, the corner of that battery module might come into contact with the neighboring module. So we have the other and typically the more preferred version of pulling off these batteries and these modules, which is the vertical pull-off method, where the battery module is just being pulled straight up out of the battery pack. And just to remind you, here is the test setup for the coming slides. First, before we discuss the details of some pull-off tests that we did in our lab, though, I'd like to put these numbers in perspective. So let's look at an individual battery module, and we'll say it's approximately the size of a shoebox, which is going to be about 30 centimeters by 12 centimeters. If this shoebox or this module has a pull-off stress of 0.1 megapascals over the entire area, and then you multiply by the cross-sectional area to get force, that's the equivalent of 3,600 newtons or 376 kilograms, which is the equivalent of lifting a full-grown horse straight up. So of course, as you can imagine, if you get 0.5 megapascals or 1 megapascal, you're looking at lifting the equivalent of 5 or 10 full-grown horses, just as the equivalent force to pull the battery module out of the battery pack. And then also to define failure modes for the upcoming study, we have 3 different modes we'll be seeing. The first is adhesive failure, which is the picture in the top here, where you can see that one substrate does not have any gap filler and the other one has all of the gap filler. Moving to the middle picture, you see cohesive failure, which is where both substrates have gap filler stuck to them. And then finally, we have mixed mode, which is the bottom picture, where you can see kind of a mix of adhesive and cohesive failure. And then you can see here our parameters for testing, as well as what we've kept constant and what we've varied. And of course, we'll explore this more in the coming slides. So let's start with surface roughness. Here we're comparing the pull-off stress of a smooth surface, which will be the fresh aluminum, and then a rougher surface with sandblasted aluminum. And as you can see, there's a 17% increase in pull-off stress required when moving from the smooth surface to the rougher surface. So we can say that this is a statistically significant difference in the 2 pull-off stresses as determined by a t-test. You can see also that the failure mode changed from mixed and adhesive failure on the fresh aluminum to cohesive failure on the sandblasted aluminum. So looking next at the dry clean surface effect, essentially here we're comparing the first use of a gap filler versus cleaning the surface and then dispensing fresh gap filler for the second time on the same surface. And as you can see here, there's an insignificant difference in the change in pull-off stress, with the failure mode changing from mixed and adhesive failure in the first use to cohesive failure in the second use. Now next, looking at E-coat, of course, some OEMs are going to be using aluminum. However, some OEMs are going to be using E-coat. So we thought it'd be important to examine both of these surfaces just to see if there's any difference. And as like the last slide, there's an insignificant difference between the pull-off stress required on aluminum substrates versus the pull-off stress required on E-coated substrates. However, you can see that the aluminum surfaces have a mix again of adhesive and mixed failure mode, whereas the E-coat was all cohesive failure. Now looking at pull rate, you can see here starting at a slow pull rate of 1 millimeter per minute, there's a lower pull-off stress. But then there is a statistically significant increase from 1 millimeter per minute up to 12 millimeters per minute. And then as you increase pull rates after 12 millimeters per minute, there's a statistically insignificant change up to 50 millimeters per minute. And looking to the right, at the 1 millimeter per minute pull rate, we saw primarily cohesive failure, but then greater than 12 millimeters per minute, it was a combination of mixed and adhesive failure. Moving to bond line thickness, there actually is a statistically significant decrease in pull-off stress, moving from 1 millimeter to 2 millimeters and from 2 millimeters to 3 millimeters. In this testing, the 1 millimeter samples had mixed and adhesive failure, whereas anything greater than 2 millimeters had all adhesive failure. So like we talked about earlier, there are 2 different options that repair centers can use to remove battery modules. The first, which is what we've been investigating in the previous studies, is the vertical pull-off method. And the second is the edge peel method, which is now what we'll be looking at here. So as you can see, changing the pull-off location from the center to the edge decreases the pull-off stress by a significant 56%. So knowing this, the question is, well, how feasible is it to pull from an edge? If the pull-off stress is significantly lower, wouldn't that be the more attractive option? The issue, of course, is that in these battery modules, dimension W, which is the width between battery modules, is going to be very, very small. The issue, as seen in this picture on the right, is that dimension W is very small, so you risk the battery module colliding with the neighboring module. So in this thought experiment, let's figure out how high can we lift the battery X just before it's going to hit the housing wall or the module wall that's next to it. So assuming these dimensions down below, similar to those we mentioned in the shoebox problem, you can see here that as W varies, you're also getting a varied angle theta and a varied distance X for how far it can be lifted. Of course, with a wider W comes a higher lift X. Looking at the work that our lab did, they found often that the distance X in these individual, we'll call them L-bar samples, is 0.3 to 0.6 millimeters. So in that case, looking at this displacement, at 0.6 millimeters distance X, they saw an angle of separation theta of 1.4. So going back to the previous slide, this angle theta corresponds to a module space width of 5 millimeters. So this means that it seems that pulling from an edge in a battery module is feasible as long as that width W between the modules or between the module and the housing is at least 5 millimeters. So next, let's move to trend number 3, low density materials. This graph shows the emission targets that the European Union, the United States, and China are putting in through 2030. This is just a good reference point, and let's talk about why on the next slide. These emission targets are important because to reduce the emissions, the typical internal combustion engine vehicle manufacturers, or OEMs, are going to have to lightweight their vehicles in order to reduce their CO2 emissions. Of course, though, even with all this reduction in weight of these ICE cars, they still won't be able to meet the emission targets that have been set by these different governing bodies. So to truly meet all of these requirements, OEMs are starting to switch over their vehicles from internal combustion engine cars to electric vehicles. The problem, though, is that in doing this, they actually have to add weight back into the vehicle when switching over to electric vehicles. So now they're trying to figure out, well, how can we lightweight our electric vehicles? Because of course, this will improve battery range, which is something that every consumer is looking for. So lightweighting is going to replace many of these heavier metals with either lighter metals or polymers. So things such as steel will be replaced with materials like aluminum, or potentially you'll be seeing a combination of plastics like glass-filled polycarbonate combined with these aluminums to ensure that all of these components in the electric vehicles are going to be as light as possible. So then one of the ways that OEMs are going to be bonding these lightweight materials together is with adhesives. As you can see here, in the next, we'll say 9 years at this point, because this graph was made for 2010 to 2030, but you'll be seeing an increase into 67% use of lightweight materials. So they'll need a way to put these lightweight materials together with the metals. Therefore, adhesives will be used in bonding all these substrates together. So now we've talked about gap fillers a lot today. So I would like to do a case study comparing the use of a typical gap filler and then replacing that typical gap filler with a low density gap filler on an entire battery pack and seeing what difference in weight that makes. Here you can see we're comparing Cooltherm SC3500, which has a 3.3 gram per cubic centimeter density, versus SC3000LD, which is a 2.4 gram per cubic centimeter density. We're going to approximate a battery pack with the dimensions of a queen size bed, which is 60 inches by 79.5 inches. And then we're going to assume a 1 millimeter bond line. So the first thing we're going to do is switch to the metric system because American units, all right? So looking at that, we have a width of 152 centimeters by a length of 202 centimeters. So using this with a 1 millimeter bond line, or 0.1 centimeters, we have a total volume of gap filler of 3,070 centimeters cubed. Taking this and then multiplying that by the difference in densities, converting to kilograms, you can see here that by changing from SC3500 to SC3000LD, you're going to be saving 2.8 kilograms per battery pack or 6.1 pounds per battery pack. This, of course, assumes 100% coverage, and not every OEM may be using 100% coverage, so I thought it would also be fruitful to include the 75% coverage as well as the 50% coverage. So you can see here, you might see a range of 1.4 to 2.8 kilograms in weight savings by changing gap filler density on the battery pack. And finally, let's look at trend 4, alternate chemistry materials. So looking at alternate thermal management chemistries, one of the concerns that OEMs have specifically with silicones is that the off-gassing or the volatile siloxanes will affect some uncoated surface, like a door, for example. And once that door goes through the paint process, you can see that the paint won't stick and it will actually drip off the door. So OEMs are constantly pushing for ways to mitigate these volatile siloxanes. And at Parker Lord, we found there are two options. The first is to replace the typical silicone with a low volatile silicone gap filler, or the second is to replace a silicone gap filler with a non-silicone gap filler, such as a urethane material. So as you can see here on the top right, we have a different table of all of these materials that are used in situations where OEMs are concerned about outgassing of the silicones. So our combination of low volatile silicone gap fillers as well as urethane gap fillers. And just as a reminder for everyone listening, Parker Lord does offer 4 different chemistries: silicones, urethanes, epoxies, and acrylics. For our gap fillers, we currently offer them in silicone and urethane chemistries. And then for adhesives, we offer them in urethane, epoxy, and acrylic chemistries. So looking at these different adhesive chemistries, you can see here acrylic, urethane, and epoxy, as mentioned earlier. I thought it'd be important just to mention what these different chemistries are typically used to bond. So acrylics we typically see used to bond metals, but also these acrylics are great for bonding thermoplastics, especially where lightweighting is concerned. And you'll find these adhesives under the Versalock or the Lord brand. Moving to urethanes, these are typically used to bond thermoplastics as well as coated metals. And these urethane adhesives can be found under the Lord name. Finally, with epoxies, once again found under the Lord name, these can be used to bond prepared metals as well as composites. So to summarize today, we have 6 major takeaways. The first is that serviceability of battery cells or modules is important because battery cells are the most expensive part of an EV. So financially, it's better for the OEMs and for the consumers to be replacing individual cells or modules instead of the entire battery pack. The second takeaway is that Parker and Parker Lord offer serviceable seals and gap fillers for EV applications. Thirdly, non-serviceable materials are typically used between cells and module housings, whereas serviceable materials are typically used between the module and the pack heatsink. Next, reworkable materials are most easily removed via vertical pull-off, but some geometries may allow for edge peel, which could reduce the overall pull-off stress. Fifth, low-density materials will save significant weight in a battery pack application. And finally, we frequently see customers pursuing non-silicone or low volatile silicone options to combat volatile siloxane generation. And with that, I'd like to open it up for questions, but first, I just want to thank everyone for listening in, and we hope that this was valuable and informative for you. Thank you.